Hello everyone, April 12th. Alright, so the goal is very simple. We are going to do this and let's do segment 3 with lazy propagation. Alright, deal with this one first. Given two integer arrays, push and popped, each with distinct values. Return true if this could have been the result of a sequence of push and pop operations on an initially empty stack, or false otherwise. Push, pop, push, and then pop. Huh. 1000. And all the elements of push are unique. Interesting. So we have a push, we have a pop. Then we'll see I push. Well, I can just push until I I push until I see the first pop, right? And then I pop. And then we see the head. If the head is not the same, I keep pushing until head is the same, and I pop. At the end, the stack shall be empty, and we shall consume all of them. Right? Okay. Give this a shot. Okay, give this a shot. So here is my reasoning. Alright, so we're gonna have a stack, okay? And let's do I and j, right? I equals j equals 0. And we will, while I smaller than len pushed and j smaller than len popped, right? While, popped j is equal to while stack, right? And this is equal to the top of the stack. Then stack.pop and j plus equal 1, right? If not, then stack.append pushed I and I plus equal 1. Does that make sense? We'll start. If it's not, I'll push. And then we come next. Yeah, because the pop, you have to push it first, right? And then pop. And they have to pop immediately after it's been put. It's equal. If it's not, we might have new things put on. So I keep doing this until we get out. Then we say return I is equal to len pushed. Actually, they say it's the same, so I can just use n. Right? That's okay. Right. All of this can be n. And j has to equal to n. And not stack. Okay, give this a shot. This is true. This is false. Pushed, popped, validate, pushed, popped. Oh, the first one's fall. What? What happened? What the hell happened? Okay, let's print. Yeah, I like to see at the end. Okay, let's print stack I and j. Stack 1, 2, 3, 4, I pushed 4, and I put in 5. Oh, or if I is smaller than n. Yep, that makes more sense. Oh shoot, damn. What happened here? We have 1, 2, 3, 4, 3, and do 5, and then pop. Now it's 1 and 2, and never progress forward. Oh, how do we get out? Huh. Oh, I think we can do this. Right? We can say else shall break. Why? What I'm saying is if I finish all the push, right? So I plus equal 1, and I put the last one in and come up. So the last one pushed in, then I pop. If it works, then everything shall be popped. If it's not, then we shall break. Okay, 1, 1. What else can you think? Maybe push 1, pop 1, push 2, pop 2, push 3, pop 3. How about this? Some easy case. Okay, give it a shot. This is the third time we've done this, so not too shabby, yeah? $9.46. Each time the top of the stack matches the current popped, we must pop, right? Otherwise, we push new values from pushed until there is nothing to push anymore. At that time, we shall have popped everything. If not, it is not possible. Okay. Greedy. Oh, is this greedy? Yeah, I think it is greedy. Pushed. That is true. We keep pushing. We push. If we can pop, we pop. And we pushed everything, and then we see. Yeah, this is actually better. Yeah, I think the official solution is better. Okay, this is from the official solution. Better implementation, but the same idea. All right, we have a stack, and then we say for p pushed stack dot append p, right? And I say while stack and stack -1 is equal to popped j. Oh, I have a j. Stack dot pop j plus equal 1. Once nothing, we keep pushing. Right, once we're done, we should return j equal to len popped. Yeah, that is nicer. Yep. Okay, so we're done with this. All right, back to here. All right, try not to read this. Let's do this by ourselves. I thought about it a little bit last night, so hopefully the idea is right. So anyway, we have to do I have to do a few things, right? We have to do self.tree, okay? Default dict. Yeah, I like this idea of using default dict, because when you use default dict, you don't have to worry about how long the array should be. Okay, that's the default dict. And we need to say def self initiate tree. What do we need to initiate? Initiate tree, we need nums1. Don't return anything. Okay. Oh, hold on. Initiate. Nah, I will just call this. And I need to know nums1 to initiate. You know what? Let's not do it this way. Yeah, let's just do it for inside. We have tree, right? And now we'll do an initiate inside. That's okay. It's fine. Doesn't matter. Right? We just initiate. Now we don't have to pass anything. We just need, when you initiate a tree, you need the index, the tree index, and you need a segment start, segment end, right? Tree index, segment start, segment end. There's no query, so we don't have to worry about the query. Okay, here we go. So we have segment start and segment end. And what is the segment? So let's do this. N equals len nums1, right? Okay, so segment start and segment end. When you initiate tree, what's the edge case at the end? Well, if, right, I say start is larger than SC, that will just return, right? Otherwise, if start is equal to SC, then we say self.tree index shall equal to nums1 index, right? Else let's do this. If this, and only return. Oh, that is not right. Smaller than SE. No, that's usually smaller, larger than SE. Return 0. This one will return nums1 index. All right. Okay. So this is regular. So we say mid equals SS plus SE divided by 2, and then we say initiate tree 2 times index plus 1. I like from 0, 2 times index plus 1. And start to mid. We'll do that. And we'll plus initiate tree 2 times index plus 2. Mid plus 1 to segment end. And we'll say self.tree index will equal to this. Okay. So that's initiated tree. Okay, so tree is initiated. Now we need a lazy, right? Lazy equals the default dict int as well. So def update. Okay, update we have index. We have update segment start, segment end, update start, update end. All right. This one doesn't return anything. That's just the update. Okay, so how do we update? Well, first of all, we need to check to see if the current range, right? So we are looking at the current range, and we'll see if the current range needs to be toggled. And we say if lazy index is not equal to 0, or just if this, right, then we need to toggle it. And right, we need to toggle it. Now, how do we toggle? We'll say tree index shall equal to se minus ss plus 1 minus tree index. That's a toggle, right? So this one we need to toggle, so that's the toggle. And after toggle, we need to pass it down. Then we say lazy 2 times index plus 1, exclusive or 1, and do the same thing for plus 2. And then we'll set lazy index equal to 0. Okay, so that's, we finished the toggle. And then we need to check for impossible case, which is if SS is larger than SE, or update start is larger than segment end, or update end smaller than segment start. And these we just return. There's nothing to do. And if segment start is larger or equal to 10, update start, and segment end is smaller or equal to update end. So the update range completely covers the segment range. Then in that case, we need to do what? We just need to do it, right? But there's nothing. We already, if we have not done it, then we need to do it. Toggle, right? We need to toggle the thing, which means we have to do it one more time. Which means if something has toggled before, but now we toggle again, so we toggle back. So we'll do this one more time, right? We'll do this one more time. Toggle it again. And then we pass down the toggle. And, yep. And else, then we do the mid thing. SS plus SE divided by 2, right? And we do update 2 times index plus 1, segment start, mid, up, E, plus, no, not plus, update 2 times index plus 2, mid plus 1, segment end, USUE. So we do these two, and then we say tree index shall equal to the sum of what? Tree 2 times index plus 1 plus tree 2 times index plus 2. So that's my update, right? And the last one is query. Right, query. Index, segment, query start, query end. Right, this is return an integer. Again, if lazy, right? If lazy, which means we have to toggle it. Right, we've toggled it. And then basically it's almost the same thing, right? If this will return 0, right? If this, we will toggle it. It's query, so we just return. If this, we just return. If this, we will query, and then we'll return. Right? If this, we return tree index. If this, will return. Yeah, we don't have to do this. We can do this. Return query plus query. I'm not sure. It feels yeah, because when you query, you just need to do this, and then you query you push the thing down, and then you're done, right? You handled already, and then you just keep moving down. So with all these functions inside, what we need to do is we need to initiate the tree first. There's no self.tree, it's just a tree. Okay, so first of all, we need to initiate tree, which is we start from 0, segment start and segment end, segment start and segment end. That's that. Okay, then we can say for s shall equal to sum nums2. Okay, then what? Then we say for type AB, TAB, not type AB, TAB inquiries. If T is equal to 1, rest is this. If T is equal to 1, then we say update. Update what? Index. Well, we start from the front. And 0 and n minus 1. The query will be A to B. Right, I'll update. Well, if T is equal to 2, then S plus equal to PA times tree 0. Else res dot append s, and we'll return res. Not sure. List index out of range. Darn. Which one? nums1 index. That's interesting. How is nums1? How is this index? Oh yeah, it is. Because that's not the index, man. No, that's SS. Where? Oh, here. SS. Unsupported. What? Initial tree. Oh, it did not return. Trees is this. Return tree index. In that case, we can say else. Right? Oh, look at this one. Look at this one. It might work. It might seriously work. Hold on. Hold on a second. We have another. Oh, it's a runtime error. I can't even check what test cases? It doesn't matter. Doesn't matter. So initial tree update. So this is for lazy. This is a segment tree. This is for lazy evaluation, lazy propagation. Initial tree. What do we want from initial tree? Compute, right? Compute, find the total number of ones in nums at each segment, right? And update. The current node, the current segment needs to be toggled. This is the key. This is the key step. Hold on. The next line is the key step, which obtains the total number of ones in the segment after everything within is toggled, right? Basically, if there are k ones initially in a range of length L, after toggle, the number of ones is L minus K. Right, and then these are propagate the toggle to children. And this is a reset the flag for the toggle of the current node. Right. The rest is the same. Right, this is toggle again, but this time it is not due to a previously set lazy flag, right? Lazy flag, but the current need to toggle. And this is fine. Query. If there is any leftover toggle that hasn't been done, do it here and propagate it further down. That's it. The rest is pretty simple. And use default dict avoids the hassle. Right, segment tree of computing the size of the array. Okay, now is the time to see if this one works. Okay, let's check this one. I mean, it's the same thing, but it's good to just run a check again. And let's try this one. Nice. All right, nice. Pretty good. Pretty good. Well, use lazy propagation of a segment tree. Okay, yeah, it works. I mean, if you think about it this way, I think what I want to say is it's not that hard, right? I mean, there's a lot of repeated work here. Right? It's actually not that hard. But how would you, again, like the thing I didn't realize is you would do a lazy by The lazy has to be a segment. You apply the same operation, right? You apply the same operation on a range. That's the only condition you can do lazy. Right? It's not possible in my previous way of thinking. That is, you will have to change each value, and that is just not lazy. Right? You have to really toggle every single one. No, that's not lazy. So that therefore this line, right? This line is really, really important. This is how you update a whole range, right? If you are plus, right? You're doing plus. Then you can say a whole range, you have the same diff, right? But here it's different. You know what? Maybe I should put it in discussion. This is a good segment tree for myself, okay? For myself. Maybe I should put it somewhere else. Segment tree. What I want to do is be able to find this if I need segment tree. You know what? That's fine. If we need it, we'll go. Yeah, this is actually make things a lot harder. A lot harder. Segment tree. $10 minutes? No. You cannot do 10 minutes. Oh yeah, you can do it this way. Yeah, that's always. Can I search? Like if I post something, can I? Yeah, solution, I don't know. Hold on, let me see. If I post, I don't think I can search. There's no way I can search because I have a lot more right there, right? But I cannot search. So which means it's no, there's no reason to put it here. But I really like how this one turns out. You know what? You know what? You know what? I know what I need to do. So here is, yeah, I'm gonna do useful snippet, segment tree, lazy segment tree. .py. Okay. And I'll put this one here, the whole solution. Of course, not a whole solution, but we'll make some changes. So class, I can say lazy seg tree. Hi. Okay. Self tree will probably need an n, so we can put an n here. Self.lazy. No need to find the length of the tree array. Yeah, I know. Let's say self.n equals n. Well, this usually is not initiate tree, right? If it's necessary, right? If it's necessary. If this is necessary. Okay, update. Update current node with diff. Update might need to problem specific, right? Specific update requirement. Might need to use lazy index, might not. Might not be necessary. Right, we have to specify propagate to children. Reset the flag. Apply whatever update, right? Whatever update to tree, to the current tree node, to the current tree node. All right, we don't know. And then propagate. This is unknown, and this is unknown. This is fine. Query, okay. Okay, update the node. If lazy says so, right? If there is a lazy update waiting. Again, we don't know what this is, so do this. This is the same. This is the same, and then propagate the update to children. And this is reset flag, update flag, lazy flag. This is fine. This is fine. And yeah, I guess that's it. Okay, so this is not a plugin use, right? Lazy segment tree, but a well-crafted template, right? Template. When you encounter a problem that requires segment tree, it might this template might need to be adapted accordingly. Pay attention to what the lazy update refers to. For instance, the one requirement, right? The one requirement is that each update shall be applied the same to every element in the range. A common update is to add a diff value to every element in the range. Inspired by the lazy segment tree solution to problem 2569. Okay, that's it. That's good. Therefore, in the future, if we need segment tree, I will pull this out and read it, and hopefully I will be able to understand. If not, we always go back here, so they'll always help. But yeah, let's put this into a nightmare, because I really don't know how to do this. But once you know segment tree, it's actually not that hard. Wow. Okay, good. We fulfilled today's requirement. All right, and then I'll see you guys tomorrow then. Adios.